My name is Chiara, and today I'm going to talk to you about the Earth's invisible shield, the magnetosphere. Okay, so we're going to start very simply with something that hopefully everyone is familiar with, and that is with magnets. So magnets are these objects, like this one here, a power magnet, that generate a magnetic field. And it's very likely that each one of you has a magnet on your fridge. So the magnetic field generated by a bar magnet like this one is usually very simple and is what we call a dipole. As we can see, this magnetic field, we usually visualize it with the help of these magnetic field lines that tell us about the direction and the strength of the field. And in a bar magnet, we tend to have the two poles, north and the south, with magnetic field lines coming out of the North Pole and re-entering through the South Pole. And usually regions with denser magnetic field lines indicate that the magnetic field is stronger. But these bar magnets are not actually the only thing that can generate a magnetic field. We can also have electromagnet, and we have an example, a very simple one here. In this electromagnet, we have a wire, a circular wire in which current is flowing. And this current flowing generates a dipolar magnetic field very similar to that of the bar magnet. And this is due to the fact that currents and magnetic fields are very closely linked, which is something that will be important later. We'll just bring it up again. So very similarly to an electromagnet, in our planet's outer core, there is circulation of molten iron that is electrically charged. And this generates a magnetic field, which once again is very similar to that of a bar magnet. Now, you might have noticed here that this is slightly different from what we were seeing earlier because the direction of the magnetic field lines has changed. And this is because if we swap the Earth for a very big bar magnet, the south pole of the magnet will be actually located at the north geographical pole of the planet. So we can measure this magnetic field at surface, and it measures around 50 microtesla, which is actually pretty small. It's a 20th of your average fridge magnet strength, which is 1 millitesla. But this is due to the fact that we measure this magnetic field at the surface, and the strength of the magnetic field decreases quite rapidly with distance. The Earth's magnetic field is actually pretty strong, and it expands all the way into space. And we've known about this field for centuries. We've actually used it for things such as navigation, just think of a compass. But in the last 70 years or so, as a result of the spaceflight era, we've been able to study the properties of the magnetic field in space, where there's no sources of interference. And we've not only been able to study the properties of the magnetic field, but also the properties of the material that this field traps, that we call plasma. So everything above 100 kilometers of altitude needs to be studied with plasma physics. Plasma is the fourth state of matter after solid, liquid, and gas, and it actually makes up 99% of the observable universe. It makes up, for example, stars, comet tails, or lightning strokes, and the upper atmosphere, as I mentioned. So, what is a plasma? A plasma is a gas of charged particles where we have approximately an even number of positive and negative charges. The plasma that is trapped by our planet's magnetic field is mostly made up of protons, electrons, then some heavier ions like helium and oxygen that come from our atmosphere. And plasmas are unlike the other states of matter because the particles inside them are electrically charged. So particles will interact with each other. Particles with charge of the same sign, so two positive charges, will repel each other, while with particles with different charges, so a positive and a negative charge, will actually attract each other. The motion of these particles is also very strongly affected by electric and magnetic fields. And here in this diagram, you can see how the electrons and protons move in the presence of a magnetic field. So this is a magnetic field line. And you see that protons and electrons, they tend to move along the field line and also to rotate around it. We call this gyration. And so they'll move up and down these magnetic field lines of our planet. But one thing they'll be unlikely to do is to jump from one magnetic field line to the other. They'll sort of be stuck to it. And this again will be important later. So when we think about the space environment just outside our planet, we usually think of a vacuum, and that's not entirely correct. In fact, the solar wind, the sun constantly emits this stream of plasma that we call the solar wind. The solar wind is mostly made up of protons, electrons, and some heavier helium nuclei. And these particles flow at velocities between 300 and 800 kilometers per second. So they'll take about 2 to 3 days to reach the Earth. And in a centimeter cubed of solar wind, we will find only 5 particles. And this is incredibly low and much lower than, for example, what we would find in a centimeter cubed of air from our atmosphere, where we have billions of particles. So it makes sense that we think of space as a vacuum. So these charged particles of the plasma, they won't be able to jump in the magnetic field lines of our planet, and they'll actually be deflected around it. So the region, so this cavity in space created by our planet's magnetic field pushing back towards the solar wind is what we call the magnetosphere. As you can tell, the magnetic field here doesn't look like what we had in the previous slides. And this is because the solar wind is deflected, but also manages to distort the magnetic field of the planet. So on the day side, which is the side facing the sun, it will be compressing the field, while on the night side, the opposite side, it will be elongating the field into a structure that we call the magnetotail. So our planet is not actually the only object that has a magnetic field. The sun also has a magnetic field that is carried out into interplanetary space by the solar wind. So we call this magnetic field the interplanetary magnetic field. This takes a while to say, so I might call it IMF every now and then, so please remember this acronym. So the IMF extends radially, goes out radially with the solar wind, but its foot points are on the sun's surface. And the sun actually rotates on its own axis with a period of 27 days. And this rotation will cause the interplanetary magnetic field to form this spiral structure that we call the Parker spiral. So at 1 astronomical unit, which is a distance of the sun, the field will be on average 5 nanotesla. So again, very small, but this is why because we're so far from the source. Okay, so we want to know what happens when the solar wind carries this interplanetary magnetic field all the way to Earth's magnetosphere. And the answer to this question is actually depends, because it depends on the magnetic field, the orientation of the interplanetary magnetic field. And specifically, it depends on whether the fields point north, like in this scenario, or whether it points south. So if the magnetic field points northward, like in here, the plasma particles of the solar wind won't be able to jump from these magnetic field lines of the IMF to the magnetic field lines of the magnetosphere, and they'll be deflected. So in this case, the magnetosphere acts like a proper shield. And there's some speculation about whether our planet's magnetosphere is protecting our atmosphere, because some say that without this shield, the solar wind would erode it away, like it might have happened with Mars. Then instead, if we look at southward pointing interplanetary magnetic field, the picture gets a bit more complicated. In fact, in this case, we have anti-parallel magnetic field lines. So the magnetic field lines of the interplanetary magnetic field and those of the magnetosphere, they point in opposite direction. And in this configuration, we have a phenomenon called magnetic reconnection or magnetic merging. And you can see it here in this animation. So opposite pointing magnetic field lines will be able to merge in this case. And the purple line here, this is one of the merged lines. You see it has one foot point on the Earth, while the other one here will be connected all the way back to the sun. And so as you can imagine, the plasma that was dropped on this magnetic field line of the interplanetary magnetic field will be able to flow inside the magnetosphere now. So there will be a transfer of mass and energy from the solar wind to the magnetosphere, which is very important. So magnetic field lines merge here on the day side, but they're also influenced by the solar wind that keeps coming in. So this solar wind pushes these newly merged magnetic field lines towards the tail, and this is where they accumulate. The accumulation of magnetic field lines here causes some pressure in the tail, which is indicated here by these gray lines. And if you look here, you'll notice that the northern part of the tail and the southern part of the tail, the field lines have anti-parallel directions again. So as the pressure pushes them together, they'll be able to merge again here on the day side. There's another merging point. So these newly merged lines, they'll have both foot points on the Earth, on the two poles, and they'll be able to circulate back on the day side. So this is a cyclic process that we call the Dungy cycle, and it will keep happening until the IMF goes back to being northward. And you can see there's the Dungy cycle involves the circulation of these magnetic field lines and of the plasma stuck on them. So it causes a lot of activity in the magnetosphere. So something I've been looking at during my PhD is what happens when we go very rapidly from northward to southward IMF. What goes on in the magnetosphere? We expect that under northward IMF we'll have this relatively quiet system with not much mass or energy entering the system to a highly driven system with, again, this circulation of field lines and plasma. So there are many processes taking place as a result of that, and we can study them both from the ground, but also in space. But we'll start at looking at what we can see from the ground. So first of all, you need to know that there are many current systems flowing in the magnetosphere, but also in the ionosphere, which is the utmost layer of the atmosphere, which is also made of plasma. And these currents are strongly affected by changes in the magnetic field and in the convection that you see here, which is what I mentioned earlier. So as the IMF turns from northward to southward and the Dungy cycle begins, the currents in the magnetosphere and ionosphere, they will change as a response to this. And these changes in the currents will in turn generate some magnetic disturbances. And this is something that we can measure from the surface. We in fact have many networks of ground magnetometers. You can see some here provided by the SuperMag collaboration. And we have magnetometers both in the north and south hemisphere, measuring these disturbances at all latitudes as well. So they can tell us about the processes that happen in the magnetosphere. But what are these processes? So an example is a substorm. So if we go back to what I was saying while I was talking about the Dungy cycle, when we have south or IMF, we have reconnection here on the day side, and the merged lines here in purple are dragged back to the tail. Now, in the tail, they don't need to merge straight away. They can actually accumulate more and more until there's this explosive merging happening. The plasma stuck on these magnetic field lines after the merging will be accelerated back towards the Earth. And as you can imagine, these energetic and charged particles, they will interact with the neutral particles that we have in the atmosphere. And they'll be giving rise to phenomena such as the northern-southern lights. This is something that you can see here. This is technically not ground data. So this is data from a NASA mission called Polar that observes the aurora oval, which is a structure here. So you can see here, the aurora oval looks pretty similar in these snapshots up until this time, where we have a substorm. So this explosive reconnection in the tail, where we have an enhancement in the thickness and brightness of this aurora oval. And if you're wondering why this is an oval, so this oval is the region in both the north and southern hemisphere where we're more likely to observe aurora. And this is because these magnetic field lines, their foot points, will create these oval structures around the polar caps. Now, the substorms are a magnetotail phenomenon, and so the disturbances that we detect in our ground magnetometers, they'll be at high latitudes and they'll mostly be concentrated at longitudes near the tail. There's then another phenomenon that we can observe with ground magnetometers, and this is geomagnetic storm, which is different from substorm, which are different from substorms. So geomagnetic storms, they are, oh, we got this here. They're caused by the intensification of one of the current systems I mentioned earlier, and they manifest themselves as a decrease of the magnetic field that we measured on the ground, especially at low latitudes. And they're caused by long periods of south IMF, so at least a few hours. These are not as common as substorms, and they are often associated with something you might have heard about before, which is coronal mass ejections or CMEs. CMEs are these large ejections of plasma from the solar corona, which is the solar atmosphere, and they're usually associated with long periods of southward IMF. So here you have a coronagraph from the SOHO spacecraft, and with this instrument, we covered the solar photosphere, which is the solar atmosphere, which is very bright, so that we can see the corona here. So right here, you see this large eruption, and that's exactly what the coronal mass ejection is. So you might also be familiar with the 11-year cycle of solar activity. So a near solar maximum that we're actually approaching in the next year or so, we tend to have more coronal mass ejections from the sun, and so we expect to have more geomagnetic storms. We had two big storms this year, for example, where we could see the auroras in the UK as well, and that was one last month and one in May. But so not all aspects of this interaction between solar and the magnetosphere can be observed from ground magnetometers. Sometimes we need to rely on spacecraft data. One example for which they need spacecraft data is this. So going back to the G cycle, when we have a southward IMF and reconnection here on the day side, magnetic field lines are then dragged to the tail and they accumulate there. But here on the day side, we'll have a weaker magnetic field. So the magnetosphere will be weaker when pushing out against the solar wind. And this will result into the magnetospheric boundary, which we call the magnetopause, actually moving inward towards the Earth, which is what you see here. So this magnetopause is basically the region where we have a balance between the solar wind pushing in and the magnetosphere pushing out. So this is quite important. And the change in distance of this boundary can actually be quite significant. So under quiet conditions, the magnetopause here is usually at 10 Earth radii from the Earth's surface. And an Earth radii, just for context, is 6,371 kilometers. After long periods of South Rayma, the magnetopause boundary can get down to 6 Earth radii. Now, you might be familiar with geosynchronous orbit. Satellites on this orbit, there's a lot of communication satellites, for example. They orbit the Earth with a period of 24 hours, so equivalent to our planet's rotation. And therefore, their projection on the planet's surface is always on the same point. This orbit is located around 6 Earth radii, so it might happen that these satellites suddenly find themselves in the solar wind where they're exposed to much stronger radiation, which can be a problem. So spacecraft crossing the magnetopause are actually something that we can use to study this phenomenon. In fact, spacecraft going from inside to outside the magnetosphere, the other way around, they'll observe changes in magnetic field and in plasma properties. For example, here, a spacecraft in the magnetosphere will observe a northward field, while after leaving the magnetosphere, will observe a southward field. And also in the magnetosphere, the plasma will be less dense, but also much hotter than it is outside. So with these crossings, we can determine where the magnetopause is located. And if we have multiple spacecraft crossing it one after the other, we can also get some information about how fast the boundary is moving. So I've just given you an example of why it's so important to study the magnetospheric interaction with the solar wind. Is not just important from a scientific point of view, but also because it affects our day-to-day life. In fact, the flow of plasma and energy into the system can have several effects, which we usually call space weather. So one space weather event that we mentioned during the talk is auroras, which are caused by the interaction between these charged particles on plasma and the neutral particles in the Earth's atmosphere. And this is the picture that I took from my house in Surrey last month during, I think, what was the biggest geomagnetic storm of the last 20 years. But not all space weather phenomena are this pretty or this pleasant. In fact, for example, satellites, as I just mentioned, might suddenly find themselves outside the protective shield of the magnetosphere. During strong geomagnetic activity, we might also have more precipitation of these charged energetic particles, which can damage the components in satellites. And this increase in energy in the system, it can cause the atmosphere to swell, causing a problem called satellite drag. So satellites will encounter denser air during their orbit, which will make them change their orbit. So this video here This is a video that was taken in February 2022, where Starlink launched a few of their satellites that were meant to reach orbit. But this happened during a geomagnetic storm, so the satellites never reached their orbit and re-entered the magnetosphere. And I believe about 40 spacecraft were lost that day. So it can be a serious problem. In addition to that, we have changes in the currents in the upper atmosphere that we mentioned earlier. And these changes in currents can affect GPS signals, causing navigation errors. They can affect high frequency radio waves, and they can also induce currents in the Earth's crust. And these currents, in turn, they can enter the power grids, so they can damage transformers and cause blackouts. And they can also cause voltages in pipelines, damaging material, so causing a lot of pounds worth of damages. So the largest geomagnetic storm or space weather event that we know of happened in 1859. It's called the Carrington event. You might have heard this name before. Back then, the main form of technology was just telegraph lines, and as a result of this space weather event, some of them caught fire. Now, you can imagine why space weather would be a problem nowadays, because we're much more reliant on technology, and space weather can cause billions of pounds worth of damages. So, severe space weather in particular has actually been added to the UK National Risk Register, and its overall impact score is similar to that of effusive volcanic eruptions and inland flooding. But space weather is actually more likely to happen, with a relatively likelihood to happen in the next 5 years being between 1 in 20 and 1 in 2, which is the same as heat waves or quality air events. So this is another reason why research into magnetospheric physics is so important. And there are actually a lot of solar wind and magnetospheric missions currently in orbit gathering precious data. But missions are keeping planned and developed. And one mission that I'm particularly interested in, SMILE, which stands for Solar Wind Magnetosphere Ionosphere Link Explorer. SMILE is the first ever joint mission from the European Space Agency and the Chinese Academy of Sciences, and my institution, which is the Mullard Space Science Laboratory, has also taken part in this mission. So SMILE is planned to launch soon in a year in late 2025, and it will have a highly elliptical orbit and will carry 4 instruments on board. First of all, it will have a light ion analyzer to study densities and velocities of these charged plasma particles. It will have magnetometers to study the strength and the direction of the magnetic field, and it will carry 2 imagers. One will be an UV imager, so this will take ultraviolet images of the aurora oval, specifically in the northern hemisphere. And the other one will be a soft X-ray imager, which will help us for the very first time to image the day-side magnetosphere. In particular, we will image this region here where the solar wind sort of piles up against the magnetosphere, and in which ions and neutral particles can interact. So the name of the interaction that takes place is solar wind charge exchange. And as I just mentioned, it takes place between ions, so atoms have been stripped of some of their electrons, and neutral particles, which have the same number of protons and electrons. So with solar wind charge exchange, these ions will actually strip the neutral particles of an electron, making them also ions. And this electron will initially be on a higher energy orbital, so an outer orbital, but it will end up decaying to lower energy orbital. So the difference in energy between the two orbitals is emitted in the form of a soft X-ray photon, which is exactly what SMILE will detect. Solar wind charge exchange was discovered a while ago in comet tails, and it's actually a process that we knew was happening in the magnetosphere. Especially X-ray astronomers knew about this because they want to observe distance X-ray sources, and soft solar wind charge exchange sort of was adding noise to their observation, so it was considered a nuisance. But with SMILE, we'll be able to use this for the very first time to do some science, which is very exciting. So this is a simulation of what we expect to see with the soft X-ray imager on board of SMILE. And you can see here there's this SMILE-shaped structure. So the mouth of the SMILE that you see here will be the front of the dayside magnetosphere here, while the eyes will be these indentations here, which we call the cusps. They're formed by magnetic field lines here going towards the sun and here going towards the tail. And there's actually a lot of penetration of solar wind in this region, so a lot of solar wind charge exchange happening. So with this sort of data, we will be able to study the changes in shape and position of these structures, especially after changes in the orientation of the interplanetary magnetic field that we've just discussed. And we're also hoping that this data will help our understanding of some other processes that we've discussed. And for example, we hope to better understand the relationship between coronal mass ejections and geomagnetic storms, but also of the evolution process of storms. So this brings me to the conclusion. So we've seen how Earth's magnetosphere is a very complex system that interacts with both the solar wind and the interplanetary magnetic field. Changes in this field, and specifically in its orientation, can cause mass and energy to enter the magnetosphere, which can then result in space weather phenomena and substorms or geomagnetic storms. So there's a lot of research currently going on in magnetospheric physics, but we're very excited about future missions such as SMILE, which will allow our understanding of these processes to improve. And if you're interested at all in space weather, there are plenty of resources out there to keep an eye on solar wind conditions. I personally use Space Weather Live on my phone. So yes, you can also do take your part in space physics. So thank you for listening. That's all from me.